So, hi, welcome back to Econometrics B. This is the second set of lectures on binary response models. I'm pretty much following closely Woolrich's textbook, chapter 15, but actually we're skipping section 15.7, which is about the specification issues in binary response models. So endogeneity, what happens when you have continuous or discrete and endogenous variables. Um, and there's some other interesting issues there about neglected heterogeneity. What does that mean for the estimate of the parameter estimates and average partial effects? We can actually talk a little bit about that today. And then also basically non-normality assumption in the latent variable model, things like that we're skipping. So this is not to say it's not important. It's just you have to read that and get that under the hood yourself. Okay. Today it's about binary response models for panel data, which is pretty much a one-to-one replication of what is going on in section 15.8. Okay, so that's kind of the plan for today. So I'm going to divide that into basically three videos: one on binary response models without unobserved effects, one with unobserved effects and under strict exogeneity, and then we're going to talk about how to estimate dynamic unobserved effects models. Okay. For the first one, we're pretty much, I mean, that's a natural starting point to see how far do we get with models without unobserved effects. What happens if we ignore the unobserved effect? Well, that depends on how that unobserved effect, the nature of that unobserved effect is. Is it correlated with the explanatory variables? Well, maybe you get inconsistent estimates in that case. Is it persistent over time? Well, like it's usually assumed to be in panel data models. Well, then maybe your variance covariance matrix need to be corrected for clustering at the individual level. We calculate robust variance covariance matrices. So, in short, we pretty much going to try to derive estimators for models models where we are not accounting explicitly for the unobserved effect, and see if we still get consistency, asymptotic normality, and what the variance covariance matrix looks like. Then after that, we move on to explicitly modeling the unobserved effect. And the unobserved effect is going to take the usual, be interpreted in the usual way. It's a individual specific persistent effect that's constant through time. And then we will try to develop models to deal with that, just like we did in our treatment of linear panel data models. And we're going to start with the static models first, developed under strict exogeneity assumptions. So here we can estimate random effects models, like random effects Propet model or the random effects logit model. We can allow for some correlation between the explanatory variables and the unobserved effect through the so-called correlated random effects models. Or we can even completely remove the unobserved effect by fixed effects models, such as the fixed effects logit. As it turns out, in deep contrast to linear panel data models, it becomes increasingly difficult to deal with fixed effects in nonlinear panel data models. There's no easy trick to remove it. You can't just difference it away, essentially because you have a nonlinear panel data model. Turns out that from the logit model, this is actually an explicit trick you can do once you do conditioning on the number of times that you observed an individual having y equal to 1. Okay. So anyway, we're going to come to that. And then finally, we're going to study dynamic unobserved effects models. And here, actually, the dynamics, if dynamics are particular of interest, say you want to find out what is the effect of, past smoking behavior on present smoking behavior, you may think that there's strong state dependence in that outcome. If I smoke today, they're more likely to smoke tomorrow. But is this due to initial conditions that I was smoking in the very first period? And is that potentially correlated with explanatory variables? Is it basically due to that unobserved effect CI? Some people just like cigarettes a lot, and the policy implications of those things are very, very different. So we really want to have the causal effect of experiencing smoking in the last period that effect on smoking behavior today. Okay, because the policy implications are very, very different. You can't really do anything about the fixed unobserved effects by moving out a guy from smoking in one period. So if you're so it's really important to get that parameter right. Turns out if you're ignoring the unobserved effects, if you're not estimating the model, accounting for that, if you're not accounting for the initial conditions problem appropriately, then you're going to have something like spurious state dependence. Essentially, the lag dependent variable is going to suck up all that persistency in the stuff you didn't model, like initial conditions or persistent unobserved effects. Okay, so it turns out to really be important to treat to model the heterogeneity in the dynamic context, where it's less important in static models. As we'll see. That's kind of the overview of what we're going through. Okay, so before we can talk about how to estimate models, we need some data. Okay, and here's annotation for the data, or for panel data. So we assume we observe n individuals over time, over t time periods. So we have data on the binary outcome YIT that takes values 0 and 1 every single period for each individual. And then we have a bunch of explanatory variables, XIT, that is also observed for n time periods, or the t time periods for n individuals. With the notation I've written here, it's a notation that it's kind of implying that we have what is called a balanced panel. Okay, a balanced panel, that is the case that's happening in the case where we have the same number of observations for each individual. And the data set we're going to look at is exactly a balanced panel data set. You can also have some things called, like, surprise, an unbalanced panel data set, where that is not the case. Okay, it could be that individual number 1 is observed 2 times, individual number 2 is observed 15 times. Okay, notation here is just going to be a little bit hairy, but not much. Really, here it's just putting a subscript I on the t, and you're kind of going in most of the cases. So there's going to be lots of sums over time periods, and there you just need to put a little subscript on the capital T, and then you're going. Anyway, so that's just for simplicity. We just use notation for the balance panel. As usual, we assume random sampling over I, but not over t. So individuals are randomly sampled. That's kind of, that's what we've done so far. We're going to still do that. Okay, but we're not going to assume random sampling over t. It could be, for example, that basically there's time dependence. Okay, so you observe the same person over time. They're likely to be very, very they have a lot of characteristics that are not that are essentially time constant, like your gender, for instance, right? I'm not going to change gender every time period. So if I'm not control for that, it's going to be in the unobservables. Okay, like the finished educations at the point where you're not changing your education anymore. That's something that's individual specific. Okay, if you're not control for that, it's going to be in the error term. So assuming basically no independence over time for cross-sectional time for the across time for our data is not really a fruitful assumption to move forward with. Okay. Well, so that's that was just a little bit of notation. Let's actually look at the real data. Okay, and we're gonna, as usual, just build on the data sets that we have from Woolridge's textbook. Okay, so what I'm doing here, I'm really just reading in the pandas. I'm reading in NumPy. I'm using this nice, actually very nice routine in the pandas module that has reads data, so that can read in a data set. Stata data set just right into a data frame. Okay, very, very simple, one line. Okay, and since all the text, all the data sets used to provide results in Woolridge's textbook is in Stata, it's very convenient to have this one. Okay, so we're going to probably use that again. Okay, so then I basically add a constant that was not there, and then here's kind of just printing out the a few lines from the data set. Okay. So what do we have here? We have the first column here. That's individual number 1. Okay, so ID here, that's the individual number, and it goes all the way down to 5,663. So there's that many individuals in the sample. But there's 28,000 observations because we observe each individual 5 times. And you could actually check if that adds up, because we have a balanced panel data set. If you get 5 times this, it's going to give that number. That's not entirely right, because we started with 0, so you have to add 1, right? So here, the data is sorted. So it's first sorted for each individual, and then for each time period. So here we observe the individual I 1, 2, 3, 4, 5 times. Okay, so that's the way the data is structured, and the way I'm assuming it's structured throughout. Then we have a binary indicator of labor force participation for this married women. So 1 means you participate in the labor force, and 0 not. Okay, so this is one that's actually time series variation in that. And then there's some variables that are not changing over time. So raised, education. So this is like final education. Age in the beginning of the sample period, that's squared. These are variables that are not changing over time. Then there's kids, which is the number of kids. And actually, there is variation in that variable over time. It's probably not the best example. I'm showing probably we can see if we say, go say a little bit further down, find some other individuals. See, we got some variation there in kids. Well, I was not lucky, so maybe maybe we find something else. I did not prepare this. There should be some variation in kids. Well, it's hard to find people just searching for that, on the run. Trust me, there's variation in kids. Otherwise, we'll not be able to identify the coefficient on that in a fixed effects regression, and I've done that. Okay, so then there is a household or husband's income, where we also have a log of that variable, and here you clearly see there is time series variation in that. Then we got time dummies for each of the 5 different time periods, and from time to time we're going to include time dummies and leave out period 1, so we don't fall into the dummy variable trap and lose identification. Then we have the constant at the end. That's our data set. Then sometimes we want to add some additional data sets, like lag dependent variables and so on. Okay? We construct them from this. So why don't we just move on? That's our data set. Okay, so then in order to get a little bit further going, I'll read in some libraries, and I'm going to return to describing them. Okay, so we need linear algebra, and we need a little bit for tabulation, and then, not to overwhelm you with code in this notebook, I've relegated some routines, some simple routines for linear panel data models into a separate Python file that is in the repository. It's called linear panel data py, and it should be in the repository, where we also find the notebook. Okay, and then there's something called index models, which is a collection of functions that, for example, have the objective functions, such as like the negative of the likelihood functions, for estimation of panel data binary response models. So both for pool probit, random effects probit, and so on and so forth. That's all embedded there. This is some code that I've just written for this purpose. Probably not as elegant as you guys can do it, but I gave my best shot. Then there's a kind of another set of routines for M estimation. So I try to write up a little module that does basically M estimation, where the input is essentially the sample objective function. We're going to look at that too. Okay. And then a little bit of renaming or naming of some list of variables here. We got YIT, which is the dependent variable. So this is what we're trying to model. So I put this into some lists, and YIT here is labor force participation for the married female. Okay, and then we got the time varying variables. That was kids. That I was not able to really show you, but you have to trust me. There's time series variation in that. And then log of the husband income. Then you got time varying, only time varying, but not individual varying variables, like the time dummies. Okay, so I stored that into XT to signify it only depends on time. And then there's a last set of variables that are time constant explanatory variables. And it's important to kind of discriminate between these types of variables because, for example, xi, these last variables, education that's not changing over time, race that's not changing over time, age, initial age in the first period that's not changing over time, these cannot be included in the effects regression. Then you lose identification right away. So that's why I kind of group them into this. Then there's the group or the cross-sectional indicator, which is the individual ID, which is the individual number that run from 1 to the 5,663. Okay, so that's just a little bit of notation. Okay, so before we actually use these data to estimate it, let's just check a little bit, check out what is it that really we are interested in modeling. We're interested in our object of interest is, as usually, the response probability. So here it would be the response probability for period t for individual I, the probability that the outcome variable is equal to 1 in that case, conditional on a set of explanatory variables for that individual at that time period, and holding constant also an unobserved effect. So if there's an unobserved effect that's persistent over time, we want to try to see if we can hold that constant too. Say if you want to get the partial effect on the response probability for changing, say, changing one of the explanatory variables marginally, we want to hold CI constant once we're doing that. Okay, this kind of means that we really want to not have these two being correlated. Okay? So this is the object of interest, the response probability. So what is a natural starting point? Like we did last time, it was a linear probability model. Okay, there's a lot of good things to say about the linear probability model. Like we alluded to last time. If you're mostly interested in the average partial effects, it's really a good starting point. So here's a linear unobserved effects model. So it's basically assuming that the probability which of YIT conditional on XIT and CI is a linear function. Okay, a linear function. That's why it's called the linear probability model. And now it depends on XIT, but also CI. And because we got a Bernoulli distributed variable, then the probability that is equal to 1, conditional on XI and CI, is equal to the expectation that it's equal to 1. Okay? So this is essentially a linear regression model that we can estimate with estimation methods we have available for estimation of linear regression models. Here, a natural choice would probably do like a linear fixed effects regression, or a random effects regression, or a pooled OLS regression. Okay, that's kind of what we have in the toolbox for models like this. Problems are the usual ones. We have the problem that the response probability is not bounded between 0 and 1. Essentially, if you let x increase, since it's entering linearly in this function, eventually it's going to go outside the unit interval. So if b is positive, if you let x increase, then it's going to be above 1. Okay. You also have a problem with heteroscedasticity. Well, it's not. I've not written it up here, but really the variance, the conditional variance here, is essentially XIT beta times 1 minus XIT beta plus the unobserved effect. And the bottom line is that depends on the explanatory variable. So when you have the conditional variance depending on the explanatory variable, you have heteroscedasticity. Okay, so that's one thing. And then also, because the probabilities can be outside the unit interval, then you also have that variance can even go negative, because x beta times 1 minus x beta plus c in that x beta, that is, if that can go, if x beta can suddenly be outside, be larger than 1 or less than 0, well, then you got your negative variance. Okay. Beyond that, you have this unnatural restriction on the unobserved effect, that it is between minus x beta and 1 minus x beta. So that's kind of, the usual problems. Okay. The advantage here is it's very, very easy to do a transformation of the model that completely eliminate the unobserved effect, so we don't have to worry about whether it's correlated with the explanatory variables, or we don't have to worry about calculating robust variance covariance matrices and so on. Okay, so that's well, that could still be a good idea for other reasons, like serial correlation in other terms, but really, it's really easy to get rid of that. Just take first differences, or do it within transformation, and there's no C left in your transform model. You can just regress transformed Y's against your transformed X's, and you'll be fine. Okay, so that's kind of a natural starting point. And why don't we try to see if we can estimate this model? Oh, I probably forgot to activate some stuff here like this. So here are the results. So what I'm doing here is really, I'm relying on this this library here I call LPD for linear panel data models. That was I talked about in the beginning. Essentially, I'm not going to cover that. We all already know how to do linear panel data models. But you can go and check it out. So I'm doing with that two different regressions. I'm doing a fixed regression, and I'm doing a pooled OLS regression. In both cases, I'm calculating the robust variance covariance matrix. I'm using as the indicator for the cross-sectional unit, the ID, so the individual identifier. And then the explanatory variable, well, that was YIT, which is labor force participation. And then for the fixed effects, I'm including only the variables that has time series variation, whereas for the pooled OLS, I also include the time constant variables. So this is what we have done. You'll see the results down here. So the first one is for the fixed effect. And you clearly see there's a negative effect of children on females' labor supply, which is kind of what we'll kind of expect, right? And the same with the log of the husband's income. If that's very high, well, then you're less likely to participate in the labor force as a female, at least in this data set. Okay. It turns out that this is kind of borderline significant. Okay. Whereas if you go down here and look at the OLS regressions, you got some really strong effects. And very significant effects that are also bigger, and actually in more than twice as large for kids, or about twice as large for kids, and it's much larger for for the log household income. And this is basically because what we have identified the effect from up here is only the time series variation in the data, okay? So we are not comparing different individuals, we are, so to say, comparing individuals to themselves, okay? So we are only using how those labor supply responses changes in responses to changes in your husband's income. Whereas down here, we are comparing different individuals with different husbands and different incomes and different labor supply. So it says, and also different unobserved effects. So it seems that these results kind of suggest that there's a potential correlation between the explanatory variables and the unobserved effect. Maybe it is so that the people who have high preferences for participating in the labor market is also married to people with very rich husbands, okay? Or vice versa, okay? I haven't thought about it, but there's certainly a correlation. Otherwise, you would both would consistently estimate the same parameter, okay? As we know from our treatment of linear panel data models. Now it's just in the context of a binary outcome. Anyway, so we're not going to talk so much more about linear effects regressions, except that this is going to be estimates of the average partial effects, just like we talked about in the previous lecture. Okay. So now let's move on to the so-called index models. And we're still in a world without unobserved effects, even though I know this is a little bit of confusing because we just, did our introduction here with unobserved effects, with, trying to control for that by doing a premature fixed effects regression. Forgive me for that. But we're going to go back to the situation without any unobserved effects. Okay, so essentially just assume it's not there. So how far do we get with this restriction, this index restriction, assuming that the response probability condition on xit is this g of xit beta. Okay, this looks very much like our model for say the probe beta the logit model that we looked at last time in the cross-sectional case. Okay, now it's just another index. How far did we get with that? So it turns out, last time we did maximal likelihood, right? Because with only this assumption, we have modeled the entire distribution of the outcome variable y conditional on x, because the outcome y takes only these two values, y equal to 1, in which case we have this, or y equal to 0, in case we have 1 minus that probability. So we have the entire distribution pinned down. But now we are not assuming independence across the different time periods. So we have actually not assumed enough to model the entire joint distribution of our cross-sectional unit, which is now not only xit, but xi1 all the way up to, ya1 all the way up to yit. Okay, so a subscript I here means the entire sequence of observations across time periods implicitly. So if we were to do conditional maximal likelihood, well, we would need to model that the distribution of that joint distribution of all those t random variables. How do you model the joint distribution of t random variables? Well, you need to also say something about, it's not enough just to say what is the marginal distribution for each of those t variables. You need the joint distribution. Okay? Now, if there's complete independence, well, you can just multiply the probabilities together, you got the joint distribution, okay? If they're independent. But we are not willing to assume independence. And without that, we don't have enough assumptions yet in order to have specified the full conditional distribution of y1 all the way up to I capital T, given xi, the same sequence of sets of explanatory variables. So, for example, you could have zero correlation. If you think in terms of the linear, in the latent variable model, where our model would be something like xit beta plus some error term vit, well, then that vit may be serial correlated over time, which would be very natural, right? If we just looked at a model where we had ci plus some, epsilon, another epsilon, ci would be part of that error term. If ci is constant over time, already there you got serial correlation. So in order to kind of move on, we need to make more assumptions in order to do conditional maximum likelihood, okay? That models in full conditional distribution of yi conditional on xi for the entire sequence over time. So that sounds pretty intimidating at this time. So the question is, could we use another estimator that conditional maximum likelihood, at least to begin with? The answer is yes. Okay, it's called partial maximum likelihood. It's my impression that Jesper did not cover that in detail. Doesn't mean that it's not important. And for now, we actually need it. The reference to Woolrich is section 13.8, where there's a chapter for basically pooled maximum likelihood or partial maximum likelihood. What we can do with that is we can actually still obtain an en route consistent estimator of beta by maximizing the partial likelihood. So it's called the partial likelihood because it's not really the full likelihood for the entire sequence. Okay, it's a partial likelihood. It's essentially just this. We are not making assumptions about how these things are correlated. We're just making assumptions about how the distribution of all the marginal distributions. So the partial likelihood is essentially just, the sample average over the time periods, and then the sum of all the individual log likelihood contributions that you have seen for linear index models before, or binary response models before. So essentially just summed all the observations. And if you think of this, it's very much like, you're treating the data as one big cross section and just, summing all the likelihood contributions for all the different observations and in both in time and for different individuals. Exactly the same objective function. Well, we're not dividing by t, but that's kind of, it doesn't really matter for the maximum, right? And then the partial maximum likelihood estimator is achieved by maximizing this guy here. One thing we need to so this is kind of a new estimator. What are the properties of this estimator? Is, you know, do we need to derive this and, you know, go through two proofs of theorems again, both for consistency and asymptotic normality? No, we could just apply the asymptotic results in chapter 12 directly, because it's an M estimator. Okay, and how do you see that? Well, we have an estimator in this form, right? That's an M estimator. It's a sample average of some objective function or average over randomly sampled units. And that's an M estimator, okay? So right there, you got a partial maximum likelihood. Inherent all the properties we already derived once for M estimators. So that's very good. We don't have to do labor again. What is the objective function? Well, that's a negative of the sum of all these likelihood contributions over time. Okay, and negative because we want to turn maximization, maximum likelihood into minimizing some objective function. So that's very nice. We can just directly apply those properties. So this means that if you got identification, well, then you have if you have identification, well, then you have a consistent estimator. It's asymptotic normal, and it has a known variance covariance matrix that has the structure A inverse B, A inverse divided by the number of observations n. So then you have your known variance covariance matrix that is easier to estimate. Okay, so this is very good. So this is what you do from if you do like a pooled analysis with partial maximum likelihood. So why don't we just take a look at how you implement that in Python? Okay, just to give like a little bit spell out what's going on. Okay, so in this Python file called index models .py, there's a bunch of functions, and here's one of them. Perhaps I should actually, you know, just show it to you there. So here's the code. So we got the one that's called no, this is not what we want. We want to have the objective function. So here, qpool, that's the objective function. This is what we have here. Okay. So basically, what it takes in is some data on y and x, and then some information about how the panel structure. This t here is a vector of numbers of time periods that each individual is observed. So this is actually allowing for unbalanced panel data. You could have like the first element was 5, and then 2, and then 3, and then 7 if different cross-sectional units are observed in different number of times. So in our data set, we have 5 every time. So it's just a 5,663 times 1 vector of 5s. Okay. Anyway, so that's the inputs, and you can choose what model you want to work with, if it's a probit or a logit model, and then what the return is. So here the return could be different things. It could be the object q, which would be the objective function. It could be dq, which would be the derivative of the objective function. It could be the scores, or it could be the Hessian. And you need all these things as input for the optimization routine when you're doing maximization, right? You provide your minimizer with what is the objective function, what is the what is the derivatives, and what is the second order derivatives. So we've seen that before. Okay, so what has changed? Pretty much nothing. I mean, it's really the same as before. We calculate the the x beta. We calculate the probability, the response probability at x given the parameters, and also the density we need for the derivatives. And for partial effects, we do this little truncation to not have problems with underflow when we take the log of the probability. We calculate the log likelihood. So this line here, well, that's essentially what we had right here, right? So I'm going to stay inside the Python code here. It's the same. So this here, that's essentially what we just had, and what inside these brackets here. And then to get our objective function, which is what we want, right? We just need to take the negative of the sum over the time series observations, and then we got basically an objective function, a vector of contributions, negative log likelihood contributions for each individual. Okay, and we do that by just summing over the time periods, and that's a function that's doing that. Okay, so if you have that, then you return the objective function, which is the sample average of the objective function for all the individuals, and then basically, basically we have this whole thing, and this is what we're trying to minimize. Okay, so that's kind of it. And then for the derivatives, well, these are also calculated. The first order derivatives are the same as last time, except that now we're summing those over all the different time periods. And these are just, these are simple high school rules of differentiation. Derivatives of a sum is equal to the sum of derivatives. So that's trivial. The same applies for the second order derivatives. So, I mean, the long story short with this piece of code is it's pretty much the same as before, except we're not now summing over t, and then we have the objective function, its derivatives, and its second order derivatives. Okay, and throwing that after a minimizer, you get your partial maximum likelihood estimator that turns out to be an M estimator, and then we can also calculate variance covariance matrices and so on. So why don't we try to use this? It's to estimate a pooled probit. So I'm gonna, there's this other function here that's called pooled, that's calling what we just had. It's calling Q pooled, the routine we just had for the pooled probit model. Okay, so I'm not expecting you to follow all the details here, but really we specified this objective function, then we throw that after our M estimator, okay, which is another set of routines. Let's look at that. The other set of routines here, M estimator, that's essentially specifying the objective function, the derivatives, and throwing that after the minimizer. In case you have a Hessian, you also throw that in, and then that's going to give you the parameter estimates, and then you unpack all the stuff and calculate variance covariance matrices and put the stuff into some structure, so you can put it use it in your output. This estimation routine is actually pretty general. It can be used for any objective sample objective function. Well, that the minimizer can kind of find the minimum of. As long as you just provide first and second order derivatives, actually don't have to do that. You can just say, you don't want to use them, and then you don't call them. Anyway, so back to the pooled probit. So this is what's going on there, and then essentially I'm just calculating some additional output, having estimated the model, like the predicted values of the response probabilities, calculate the average partial effects, collect the whole thing in a dictionary, and then I'll print the output. Okay, so that's kind of what is doing. That's a similar one for other types of estimators that has kind of the same structure. Anyway, so this is where we're going. And here's the function call that calls this function. Let's see if it works. A pooled probit, and it does. Okay, so let's go forth and back so we can see. And then we have a bunch of parameter estimates in standard errors. And again, we see now a negative coefficient of kids and negative coefficient on log of household income. And what about the average partial effects? Well, these are negative 0.06 and negative 0.07. Well, these are actually quite close to the OLS estimates, right? So let's look at go back and see what did we get with the OLS. Well, these are fairly close to those estimates. Okay, so it seems like, well, we're not accounting for the unobserved effects, so it's not surprising that we are closer to those parameter estimates we got for the pooled probit, or the pooled OLS regression. Okay, so that was how we did that. The pooled probit, very similar to probit. It's just that we need to essentially have a robust variance covariance matrix that's taking into account the clustering at the individual level when calculating the variance covariance matrix. Okay, so just to wrap up a little bit on the properties of partial maximum likelihood, it's an M estimator. It's consistent if it's identified. Well, we have probably in this particular case some issues with that, because the explanatory variables are correlated with the um, is correlated with um, with the unobserved effects. So CI and XI are potentially correlated. Um, so we may actually not identify the parameter of interest. It's technically identified in the sense that we have the objective function has a unique minimum, also an expectation, and also in the sample. Otherwise, we would not be able to minimize it. But so it's consistent if it's identified. That's the short version. That's a property of an M estimator. It's asymptotic normal and has a known variance covariance matrix. And then the variance covariance matrix, well, that is the structure of the variance covariance matrix that you see in chapter 12. Also, if you're doing vault statistics or score statistics for testing hypotheses, well, you need to use the right variance covariance matrix, those that comes from chapter 12, not those that imposes the information identity that comes from maximum likelihood, which would imply that both the Hessian and the outer product of the gradients are identical, and so we would have A equal to B, and this would make the variance covariance matrix simplify. Okay, so we need to use this more complicated formula where that both requires us to calculate the Hessians and the outer product of the gradients. But we can do it. So here's a little bit of just a comparison in this particular case of the different standard errors that you get from these using different variance covariance matrices in particular case. And actually, last time we did, I think we did first a simulation exercise, and also in this particular cross-sectional sample, there was not a lot of difference between these, but in this case there is, right? Now you got your estimator based on the inverse of the negative of the Hessian divided by n. Or you got the inverse of the outer product of the gradient. These are the two. You see the standard errors are much smaller compared to the sandwich estimator. That is explicitly accounting for the persistence in the error term due to a potential, for example, potential unobserved effect. Okay. And it makes a lot of sense that if you're not accounting for the intuitively, that if you're not accounting for the lots of these error terms are actually not are correlated over time, it looks like there's not a lot of variation because those errors are constant over time. There's little variance. So if you're not accounting for that, you're going to underestimate the variances. Okay? And you see also the clustering at the individual level going to increase the standard errors that we have to estimate. Okay, and so here you got the routine that's doing it. It's also part of this M-estimate class. Okay, so you got the either you got the inverse of the outer product of the gradient here, or you can have it's taking in the Hessian inverse divided by n to get your variance covariance matrix. Or otherwise, it's just doing this simple matrix product. So that's what you need to do. You need to do, if you're doing a pool probit analysis, you need to make sure you're aggregating the objective function over the time periods as well as the scores. But then you can calculate variance covariance matrices just using the structure A inverse B, A inverse, and using the sandwich formula. Just make sure you use robust standard errors if you're not accounting for that serial collation that's coming over. Now, just a little bit of before we wrap up this section, let's dwell on what did we assume and what did we not assume. We did not assume any unobserved effects. Well, what did we assume? We assumed there was no unobserved effects. So maybe there is. Okay, so we assumed a linear index structure. And this implied and then also a functional form for G. For example, it could be the CDF of the standard normal, in which case we would have a full probit. We can relax many of these assumptions, and we're going to focus on how to relax assumption number one. There was no unobserved effect. You can use similar non-parametric approaches. There's some nice discussion in the book about that, to relax this linear index structure or even the functional form of G. But for example, there's something called the Klein-Spadier estimator or the maximum score estimator. This is making not full distribution assumptions about this function G. So so that could be done, but we're going to focus on how to relax the unobserved effect in the following lecture. Now, one thing I also want to highlight is, what did we not assume here? We did not assume something like dynamic completeness, for example. We assumed, if we were assuming any sorts of exogeneity in terms of with correlation all the time, we were assuming contemporaneous exogeneity, really. We were only really assuming that contemporaneous exogeneity. We were only assuming really that in terms of the linear index model, if a latent variable model, if you had an error term in your latent variable xit beta plus epsilon, well then epsilon it, then epsilon it would be independent of xit, but not in other time periods. Okay, only in the same time period. Okay, so there's other types of assumptions that are a little bit more restrictive that you could make. For example, dynamic completeness, or even strict exogeneity. So this is obviously less strict than strict exogeneity. And kind of has a little bit of flavor of the sequential exogeneity assumptions that you've seen from from our treatment of dynamic linear pan-Leda models. Okay, so let's just say what is this implying, right? And so strict exogeneity is assuming that once you have conditioned for the entire if you look at the response probability for y equal to 1 conditional on the entire sequence from period 1 all the way up to capital T and the unobserved effect, then it is sufficient only to condition on the current value of the explanatory variables. In other words, the lags doesn't matter, the leads doesn't matter, future doesn't matter. Everything is captured by xit and ci. Okay. Well, we're not assuming strict exogeneity conditional on observed effect. There was no unobserved effect, so that's not really where I'm getting. So just forget about the unobserved effect for now. But we were not assuming strict exogeneity in the sense that that it's sufficient only to condition on the explanatory variable xit. So we did not specify how the dependence is across time. So if you're not specifying it, you cannot make wrong inference of wrong assumptions. So here's another assumption that's less restrictive. It's called dynamic completeness. And here, basically it says, if you have the probability for y conditional on x and the past, then everything here is irrelevant once you have conditioned for the current value of the explanatory variable. In other words, the current value of the explanatory variables is a sufficient statistic for the entire past. Okay. Now, this actually does not rule out that lags can be, or the explanatory variables or the dependent variable can be part of x. Okay? Or whereas that's actually the case down here. A few words more about dynamic completeness. So we are not, it does not imply independence, this assumption here. So xit can actually include lags. Okay, it's easier to justify when it has lots of lags. Okay, and you can actually also test it by simply just estimating a model where you have, say, labor force participation regressed against kids and kids last period and the period before and so on. And in the end, you would have modeled you have the entire history. And then you can test if those lags are significant, or then there's some other tests for dynamic completeness. And so this, you can say the more lags of y and x you have inside it, or for the exponential variables you have in endogenous variable you have inside x, well then it's easier to justify the assumption in some sense. So why am I talking about all this? I'm talking about it because models under dynamic complete models are inference is still valid using the same variance covariance matrix as you get from maximum likelihood. So the partial maximum likelihood estimator has the property for dynamic complete models that the outer product of the gradient is equal to the Hessian, and so you got the simple variance covariance matrix. So in those cases where you have accounted for the entire past, you're sure about that, so you don't have that dependence, then you can still use the ordinary variance covariance matrix. So it's kind of, it's just good to know. It's maybe a little bit more at the academic discussion. I think the key thing here is, if you're doing some kind of pooled analysis, even if you have lags, do the variance covariance matrix robust, cluster at the individual level. It's important. Otherwise, it's going to look like your estimates are much more precise than they otherwise would have been. Now I'm going to leave it there and then turn over to the next video, which is going to be about unobserved effects models. In particular, we're going to look at the random effects model and a random effects model, or probit model, and fixed effects models that are valid only under the assumption of strict exogeneity. Okay? So that's it for now.